When data scientists want to train new models, they have a general idea of how the flow will look like. Assuming that the problem they need to solve is well defined, they need to explore the data, define labels, visualize, train, evaluate, tune, test. The most time-consuming and often tedious part is data preprocessing and preparation. If you don't invest enough in this, you may still get a decent or even a good model, but is that enough? What if I told you that there is a case that is often unnoticed by data scientists, and by adding this small step, you can improve your model results and get a great model? In this talk, I present a problem that is often being ignored, why this happens, and how you can solve it in different ways in all possible domains. After this talk, you will add this phase to your preprocessing toolkit and won't look back. So hello, my name is Rada Menczel. I am head of machine learning in a unicorn cybersecurity company, when I lead a team of data scientists and I'm responsible for all aspects of the machine learning models in the company. I have a Master of Science in Information System Engineering from BGU, with specializations in machine learning and recommender systems. And I have more than 10 years of experience in machine learning industry, especially in cyber and fintech domains. At my spare time, I enjoy cooking many stuff, especially pizza. So I want you to think about building machine learning models like making pizza. You start with different ingredients, which are our features, and you end up with a hopefully tasty pizza, a great model. But what happens along the way? You probably ask yourself, what is she talking about? What pizza got to do with machine learning? Whether you want to get a good machine learning model or a tasty pizza, you need to follow a predefined process of rules or a recipe. Each of them needs to be completed in the correct order. For example, you can't add the cheese before you prepare the dough, and you can't cook the pizza before you add the cheese. And if you do, then I think it doesn't taste as good as it can be. The same with machine learning models. You need to pre-process all your features before you start training. Think about the features like ingredients. Each feature requires a different treatment and pre-processing. Some need wet-hot encoding, others require normalization, or even no pre-processing at all. Like in pizza, some ingredients need to be chopped, sliced, or diced. Others require heating, and some just need to be put on top. Once all the features are ready for learning, you can proceed to training the model, and only then to testing it. And if all went well, you can serve it to production. Now let's talk about data science. I'll talk today about the machine learning pipeline, and I'll focus on the pre-processing stage and show you something that I noticed that data scientists almost never check, but they should, and so are you. First, let's briefly discuss the machine learning pipeline in high level. We start by getting raw data from different sources, so we must process the data until it is ready to use by our machine learning algorithms. The process of preparing the data usually consumes most of the time. Each of the features should be examined and carefully treated, applying to each of the features different pre-processing methods. This is an ongoing process that is completed once all of the features were processed. After this step is completed, the data scientist continues to choose a machine learning algorithm and train it on the data. This is also an iterative process that is continued until the data scientist reaches the desired results. Then, the model is validated and tested in other environments, and if all goes well, it is deployed to production and monitored there. The heavy and most time-consuming parts of this pipeline are the preprocessing and training. Today, we'll take a closer look at the preprocessing phase and see what we were missing. We have three main steps of data preprocessing. First is cleaning. Here we are getting rid of possible errors and bugs in the data. Data that was mistakenly truncated, wrong values like text in numeric fields, empty ID columns, etc. Second one is transformation. In this step, we are transferring the feature using various techniques like normalization, wet-hot encoding, binning, and so on. Lastly, dimension reduction, another step of removing redundant data or reducing the number of features. Usually, this step is performed by feature selection or linear and nonlinear approaches. Let's focus on the cleaning phase, which also focuses on three main steps. How do we handle missing data? Common solutions are: first, ignoring these records. This solution is mostly used in specific domains when you have a lot of data. In other domains, every bit of information is important, so you might not want to go with this solution. The second solution is filling a predefined value that will represent the missing value. It might differ between the features, but usually for simplicity reasons, it will be the same constant value. The third one is filling in with a computed value. It can be the mean, median, or more complex equation, so each missing value we will calculate it differently from feature to feature. Then we need to handle noisy data, which is done by possible solutions. One is removing outliers manually or use machine learning algorithms to detect outliers, and by performing binning on numeric features or clustering on categorical features with many values. Lastly, for handling inconsistency in data, we can use external references for resolving the problem or use domain experts. Can you tell me what we didn't mention that we should check? The problem is data collision, where identical feature vectors have different labels. This might be a symptom to a bigger problem, that there are bugs or corruption in the data. But if that is not the case and the data is correct, then this will confuse our algorithms. What are they supposed to do with samples that look exactly the same but have different labels? What would you do? Let's take this example in cyber domain. The data is represented in a tabular format. Each record represents a file, and each column is a different feature of the file. We have here the file type, the file size, and the operating system. Of course, in real life, we have a lot more features. Take a look at these records. They have the same feature, but different labels. What we don't see here is that they came from different files, so they actually represent different files in the system. One of them is malicious, and the other one is benign. Now, let's see how we can tackle this problem. First of all, we can remove collisions. And if they are very rare in the real world, this might be fine. But what if that happens a lot? We also might be removing interesting cases here. The second solution is keeping only the records that influence the metric that are most important to us, and removing the other records. For example, in cybersecurity, we want to catch as many malicious files as we can, meaning we care about our true positive rate. However, the most painful is the false positive rate. We want to keep it as low as possible. So in this case, we will discard the records that are being labeled as malicious and keep those that are labeled as benign. The third and better option is to add features until we won't have collision. This is not always possible and can be very time consuming, but if we can do this, we'll have a better representation of the data, since it should differ somewhere because it has different labels, and get better machine learning models. Let's take the same example as before, but now let's add in the file path. Of course, we can't use it as it is right now, so we need to process it and extract features from it. Like if this is a home directory, temporary file path, entropy, and so on. There are actually quite a lot of features that can be created here. Let's do a short recap on the solution. The first is removing all collisions. The second solution is keeping the records that are more important based on our measures. And the third one is adding as much feature as possible to avoid the collisions. I had a similar situation at my work. I had many collisions in the data, and I had billions of records. And because of that, I got really poor model results. I chose the third option, and yes, it wasn't easy and took a lot of time, but it improved my model's results by 35%. I ended up with a great model that exceeded expectations and requirements from product, so that is always a plus. In this talk, I presented the preprocessing data phase in the machine learning pipeline. We talked about the existing steps and went over the checks the data scientists usually do. I presented an issue that can occur many times but almost never checked and may cause degradation in our models. Next time, you will add this check to your preprocessing toolkit and won't go back. At the end, I just want to say that you can't buy happiness, but you can't buy pizza. Oh, I meant machine learning model. And that's kind of the same thing. Thank you for joining my talk, and feel free to contact me on LinkedIn and share your thoughts. And I hope you'll enjoy your pizza.